Okay, I guess we slowly going online. Let me just like double check if things are working, and seems like it's also working on YouTube, so I can go on full screen. Yeah, so welcome everybody who is watching us on YouTube. Sorry for a few minutes of delay. Yeah, so today we're gonna have our regular hacking machine learning event. For some of us are based here in Munich, but we also have people all around the globe who are watching this stream. And I'm really excited to have Kshitiz today talking about reinforcement learning and also how to use like TFAgents. Because I think there's been some conversation about reinforcement learning for a while. I mean, this is not completely topic from yesterday, right? But TFAgents, I think, is something that a relatively small amount of content that I've seen like on the internet. So I'm really looking forward to see what it's going to be about. And since it's, you know, the format of being like online and having people from all around the globe for us is also relatively new. I think we did maybe 3-4 events altogether. We're still experimenting with different setup, right? So one of experiments that we're also trying to do is a bit of hangout party, as we call it, and essentially it's very similar as like hallway conversation as you do like in a meetup, right? So in the beginning we would have like a talk of our speaker, and after once we're done with the official part, you're gonna have like a short hangout session that people can just like, you know, join with their video and ask some questions what you usually would do like on a meetup, right? You just like go around the speaker and do it. For those of you who maybe not coming from meetup, but you found it from some other places, when we were like, you know, offline and meeting like in person, we use a meetup, or we started to use like meetup basically, and it's for us it's like still like a primary source of communication basically. This screenshot is like relatively funny, but relatively old. Here you can see that we only 600 members. In reality, right now we're like 2,000 plus members on Meetup, but it's still like a communication that we use. We also have a Slack channel, and the idea of that it's not only, you know, those events that you have like once a month or every second month, but also continuous learning that does bring like the biggest effect, right? So if you found some interesting content, right? You found maybe some other team members who were like asking exciting questions. Just go to the Slack and maybe continue your learning, stay in touch with those like people who you can accelerate your learning. Just don't be it once a month, because in this case, like your learning curve is like really slow basically, because your iteration cycle is pretty slow. Just a couple of other things. That's how it used to be looking when we were in online, or sorry, like on-site, right, in the real life. We meet up in different locations. In this case, it's just like Stylite, and we, you know, mix and mingle and talk about machine learning and topics I like. That's how it looked one of previous times when I was just like at home with 2 screens and streaming people, our speakers from around the globe. But I believe that this also gives us a good opportunity to get completely different perspective, and also get availability of speakers that before were pretty hard to do, right? In this case, Kshitiz is actually based quite some kilometers away from Munich, right? It's close to Nepal. And for us, yeah, it would be like pretty hard to just bring him like for evening for Munich to talk about reinforcement learning. And here we go, like now it's pretty easy, and we can do it in a matter of one evening basically. So I guess it's like really positive. So as I said, talk is going to be about deep reinforcement learning, and he's going to bring a couple of examples why it's helpful, and how it's easy to actually use TFAgents, and what are the pros and cons. And I mean, you can see it like just in a bit. We also use GitHub to share the slides afterwards. Sometimes it takes longer, sometimes it's just after the talk. So please sign up there if you're interested to see the content. Another way to get the slides as well is following our awesome speakers, many of them using Twitter. So you can just like get it from the first hands directly from them. Yeah, a couple of last slides. So when we meet in offline, or when you used to meet in offline, we usually have some people or companies to sponsor us, to buy some pizzas, and give us some space, basically, to have this location to get together. Once we moved online, we didn't really need to have so many requirements. But if you still want to support your machine learning community, local here in Germany, Munich, or international as we are right now, please approach me on any channels, and we can figure out how to make it convenient, right? I mean, pizza used to be nice in the offline setup, but maybe you can find some online replacement for the pizza, basically. That's more or less it. We don't yet have like a pretty strict event for the next one, but I have a couple of interesting leads. So potentially, stay tuned on our channels, and we will get updates like to you. Last but not least, all of the stream you was likely watching on YouTube, and there is also YouTube sections basically where you can ask your questions, and after those questions going to be used to a speaker like end of his talk basically. So with that, I think I'm done with my introduction, and I'm more than happy to give the mic back to Kshitiz. Let me just remove my screen, and now I'm adding you to the live stream.
Hey everyone, thank you so much, Aki. Okay, so let me just switch over to my slides, and maybe then I can introduce myself a little bit and get on with the session. So let me just do that. Yeah, and here we go. I hope everyone's seeing this. Okay, sorry about that. Let me just start from the beginning. Okay. So, like Sergey said, today's session is about deep reinforcement learning with TFAgents. And before we start, let me briefly introduce myself again. I'm Kshitiz Rimal. I'm from Nepal. I'm a Google developer expert on machine learning, and I'm also currently head of research at AI for Development, which is a not-for-profit research organization based in Nepal. And we aim to do a lot of community-based projects on deep learning, and the projects that, on AI or deep learning that can positively impact our society. So projects like AI for accessibility, AI for disaster relief and response, and things like that. So if you like to contact me and learn more about the organization or things that I do, here are my contact details, my email, my Twitter handle, and my LinkedIn handle. Feel free to reach out to me. Okay. Let's get started with the session. So the session has a bit of a disclaimer. So this session is more like an exploratory exploration towards reinforcement learning. And as I've been involved with machine learning and deep learning for a while, reinforcement learning and deep reinforcement learning specifically is a bit new to me as well. So I wanted to explore that field. And while exploring all of these concepts and terminologies, I stumbled upon TFAgents, which is also a framework for reinforcement learning. So this session is more like what I found about reinforcement learning and deep reinforcement learning, and how the things on the internet, like it can be a little bit challenging if you are new to all these new technologies like machine learning or deep learning or reinforcement learning perhaps, and things can quickly get overwhelming. And so this session is my attempt to explore these concepts little by little and break it down into simpler terms, and while doing so also explore some of the ways we can use and implement these algorithms for reinforcement learning using this framework called TFAgents. So the bit of the overview here. So the first we'll briefly talk about supervised learning versus reinforcement learning, and what are the differences and why we need reinforcement learning. And then we talk about learning deep RL or deep reinforcement learning with TFAgents, and some of the ways, some of the steps involved building such algorithms using this framework. And then finally we train the algorithm and we visualize the results. And at the end I will also share some of the things that you can do after the session, like where you can go next to learn more and things like that. So let's get started. So let's first talk about supervised versus reinforcement learning. So we all know, like if you're already familiar with deep learning or machine learning in general, you might know that this is a deep learning is basically a form of supervised learning. And what I mean by that is that in supervised learning, we aim to solve any task, or we aim to train an algorithm to learn certain tasks by giving certain examples, and these examples are in the form of labels. So in this case, in the slide you can see there are a few examples here. One is on image classification, where the app that uses a deep learning model is classifying certain object on the screen, like in this case of a paper currency, and giving us the label, how much the currency is. And another is the object detection example, and the third one here is the post detection example. And all of these tasks are supervised learning tasks because they are trained in a way that the algorithms, they are learning from labeled examples, and the dataset that are used to train such algorithms have a separate labels associated with them that makes them supervised tasks or supervised learning. Now, there are, and these supervised learning algorithms or deep learning or machine learnings, they are all built using frameworks such as TensorFlow. And if you are already familiar with machine learning, that you might have heard of this TensorFlow framework. And if you're a beginner, then TensorFlow is basically an open source machine learning framework by Google, and it enables us to build this machine learning and deep learning algorithms easily and effectively. And there are some challenges associated with supervised learning or deep learning, and these challenges are mainly in terms of labeled data set. So there will be times where it is very difficult to gather labeled data set, and if your task is more complex than just image classification on common day objects, then you might have to manually label your data so that you can train your algorithm on it. And it's very hard and a time consuming task to label your data set, and it's one of the painful tasks in deep learning or machine learning to get a labeled data set, pre-process them and things like that. And it's also sometimes tricky to frame your problem in terms of features and labels, and that is specifically true when it comes to certain tasks like decision making. So sometimes it is also beyond the scope of your label data set to make this task supervised, and that can accurately frame your problem and will work like you intended. So it's very challenging to tasks such as decision making, and to solve such challenges we can employ reinforcement learning. And what is reinforcement learning? So let me try to explain to you by giving one of the slide from the course I took a while back. And here's this slide, and this course is from Coursera, and it's specialized in reinforcement learning. So I think this picture, this definition accurately somehow portray reinforcement learning. And so there's this famous saying like, give a man a fish and he will eat for a day, and teach a man to fish and he will eat for a lifetime. So the lecturer here has tweaked the saying a bit, and try to accommodate where the reinforcement learning will fit in that. So the new version of this is like, give a man a fish and he will eat for a day, is specifically true to good old fashioned AI, and like dictation or programming, or where you type everything, where you program everything, you give instruction to your algorithm and it will do just like you have written. So this is like a good old fashion of doing things, like programming in older days. And teach a man to fish and he will eat for a lifetime. And this is true for supervised learning, where we will teach our algorithms in a supervised task with a labels data set. And in terms of reinforcement learning, how we can tweak this one is like, give a man a test for fish and he will figure out how to get fish, and even if the details change. So this is true for reinforcement learning. And in this case, what it means by giving a man a test for fish is like giving a reward of certain thing to your algorithm, so that the algorithm will not learn directly from examples, but the algorithm will get a sense of what the task is and how to do the task effectively by accumulating more and more of such a reward, or in this case of a test of a fish. So let me explain this concept of reinforcement learning even more elaborately with an example of a fictional game called Dog in a Park. And I think while I was also learning about reinforcement learning and deep reinforcement learning, there were so many courses and so many blog posts, and all of these terminologies were quite overwhelming for me. So to learn by myself, I try to create some fictional game, and I like to break down these concepts to this different part of this game. So this is my attempt to visualize certain concepts and explain to you how the reinforcement learning is in terms of a fictional game called Dog in a Park. So let me give you a brief overview about the game. The game is pretty simple, and uh, so we have a section of a park, and our player here is a dog here, and the task of our dog is to get to this X marker as soon as possible, because he's in a section of a park where he should not be. And to make tasks even tough, there are some robots placed in that park. So whenever accidentally, if the dog places himself over this robot, then he will get caught, and there will be some penalty associated with it. And there are also some bones in the park, and our dog is a very greedy dog. So what we want to do is that we want to collect as much bone as possible and get to the end of this park, this section of the park, and while doing so, avoid all these robots that are placed here in this park. So this is the basic rule of the game. And this game specifically is an episodic game. So what I meant by an episodic game is that after finishing certain steps, the game repeats itself. So when the dog manages to reach this X marker, the game will reset and start from the beginning. So this is a one episode from start position to end position. This is called episodic game. And in terms of reinforcement learning, we try to differentiate tasks in terms of continuous task or episodic tasks. So for example, if you're trying to teach a robot using reinforcement learning how to walk, then that can be a continuous task. So there could be no end to the process, and the robot can go on and walk ahead, but in terms of games like this, it is a episodic task, because after reaching certain state of the game repeat or ends itself. So this is an example of episodic task. And the player here, the dog, is an agent. And what we are trying to do is we are trying to train this agent how to take effective steps so that he can avoid all these robots placed in the park and get bones, collect as much bones as possible, and get to the end position and section of the park as soon as possible. And these are called agents. So in reinforcement learning, there are this terminology called environment. So what it means is that the park that we are talking about, where there is a player, there are these bones, there are robots, there are this end position, all these things that are in the game, they are called environment. So environment comprises of all these things: the player, the obstacles, and all the things. And in reinforcement learning, we might heard of things like states, step, action, and observation. So let me break it down to you a little bit about what they all mean. So for example, our player, the dog, is in initial position. So this is a first step. Right now, the player, the agent, they haven't taken any step now. This is like initial start of the game. So we can say that when the dog move right to the section of the park, then the state of the game changes from this initial state to the second one. So in this case, this is the initial state and this is the second state. So in this case, the term state and observation is one of the same. So whenever an agent or a player, in this case the dog, takes certain action in an environment, the state changes. So what it means by taking an action is whenever the dog moves around in this environment, whenever the dog goes up, down, left, and right, there is certain action. So in one step, the dog can only take one action, and whenever that action is taken, then the state transition from one initial state to the another one. So this is the breakdown of all these little concepts used in reinforcement learning. So we talked about environment, we talked about agents, we talked about action, that is the movement the dog can take in each step. So in one step the dog can only take one action, and whenever the dog takes a certain action, the state changes from one state to another one. And to train an agent in reinforcement learning, we need reward. So basically, reinforcement learning is like training your agent, training your learning algorithm by giving certain reward. So by observing the reward in each step the player takes, the agent will learn whether to take that action or not. So in case if the dog manages to place himself over to this position of the bone, then there will be a reward of 1.0 integer, positive 1.0 integer. And normally the rewards are scalars, they are negative or positive. So in case of negative reward we call it penalty, but in case of positive it's basically a reward. And whenever we want to train our learning algorithm to repeat certain tasks or keep doing that, then we can associate positive rewards while doing that action. So in this case, if our agent somehow manages to place himself over to this positions of the bone, then we can associate a certain positive reward while doing so, so that the learning agent can repeat that task over and over. And whenever accidentally if the dog places himself over to the position of a robot, then the game resets and gives certain penalty or negative reward, and that way the learning algorithm will know that okay, this steps should be avoided. And whenever the agent if places himself to this end position, then we can associate maximum reward or maximum positive reward. That way the learning algorithm will know that okay, the end goal, the maximum reward I can get is by reaching to this point, so I should try to figure out how I can get there, so that I can maximize the total reward I get at the end of the game. So these are all these little terminologies that we use in reinforcement learning. Okay. Yeah. Okay, so in case of reinforcement learning, like I said, we talked about environment, we talked about agent, we talked about reward. And what we are trying to do essentially is that we are trying to train our agent so that the agent can take effective actions in this environment that can maximize this cumulative reward, the maximum reward the agent can get at the end of each episode. So that is the cumulative reward or return in reinforcement learning. So when what we're essentially trying to do is train our agent so that by the end of one episode, the agent can collect as much reward as possible. And to do that, we are using in this case a deep neural network, and in this case we're using deep Q network. And this deep Q network will help our agent to give idea on what action to take next whenever the agent is in a certain state. So if we go back a little, so if our agent in this position, then this deep Q network will help our agent to go down a bit so that it can take this bone and get extra reward while placing himself over to that position. So this deep Q network will help our agent to take what action action next, and so that the reward can be increased. And this is the essentially the diagram what we use in reinforcement learning or deep reinforcement learning while talking about agent, environment, and reward. And so these are the high level concepts that we use in reinforcement learning. So let's talk about TFAgent a bit, and let's get to the point where we can use this TFAgent framework and implement this game and train our dog so that it will learn to get to this final person as fast as possible by collecting as much bones as he can. So the higher level diagram associated with TFAgent is like this, and I know this is a bit overwhelming because there are so many components used here. So I will try to break it down all of this component little by little, and by the end of this session, hopefully you will get a bigger idea, a bigger picture of how all these components work together and how we are training our agent by using all these components. So So let me first talk about, before diving into all of these components, what we actually need is an environment, and this environment is actually the game. So what we need is we need to create a class, a Python class, where there are game logic. So this game logic can be like what happens when a dog goes beyond the boundary of the park, or what happens when the dog places himself over to the robot or a bone. And we need to program all these things, and these are the basic game logic that we can create using Python class. And we can use the same game logic to create an environment, and this environment will help to train our agent using this game logic that we will just create. So first thing first, let's create a game logic class. So to give you a higher level idea of how this environment and game logic class work, so this is a kind of diagram that I have prepared so that you will get a gist of how these things are connected. So first we'll dive into this game logic class, and essentially they have we have in this game logic class, we have these four methods, that is init method, reset method, and a custom method that will tell us if the dog, wherever the dog is, if it's the last position or the end position of the park or not. And a method called move dog that will move our dog to certain position that we passed as an argument. And we have a TFAgent class where we'll also have init method, reset method that will essentially call this game logic class method. And we have an important method called step method, which I will go in a bit. So first let's talk about game logic class. So in game logic class, we can call this game logic class whatever we want for, but in this case, in this example, I have called it dog adventure. So in init method of this class, what we can do is we can initialize basically the environment of our game. So for the sake of simplicity, we know that this our game is a grid-like game with a two-dimensional visualization. But for sake of simplicity, we can program it in terms of 1D array. And while visualizing it, we can easily reshape the array to 2D, and then we can see the movement of our player. So for the sake of simplicity, I have visualize the array as a 1D array, and we have 36 positions signifying each position in the environment. And what I have done is simply I have associated numbers for each of the components that are there in this game environment. So if you want to signify the position of our player or agent, we can simply say that signify that with the number 1. If you want to signify the position where there are bones are positioned, then we can signify them as number 3. So these are all the locations where the bones are placed in our park. And in all these positions in this state variable, which is a 1D array with 36 positions, we can place number 3 to each of these positions, so that these are the position for a bone. And similarly for a robot, we can give a number of 2 and place them in these locations. So it's with simple like that, we can design a simple 1D array that will have our environment, and we can associate integers to give an idea of a dog, bone, or a robot. And we have a flag called game ended flag, and that will signify whenever the episode is over. So whenever the dog places himself over to a robot, then that will be an end episode, because that's a wrong move. And whenever the dog tries to move beyond the boundary of the park, then that could be also like an end position, and we can signify that by setting this flag to true. And whenever the dog places himself to the end position, then we can say the game is finished, and we can signify this flag as true. Similarly, we can set a reset method where we will basically reset our game to the initial position. And is a spot last method where we will check if the dog is in the last position. And we have an important method called move dog method, where we'll have current position and next position as argument. So whenever we passed our current position and the next position for a dog to move, we can check if the next person is the last person or not. And if that next person is the last position, then we can say, okay, the dog is in the last position and the game is over. And whenever the dog tries to move outside the boundary, we can return a response called illegal move, and end the game. And similarly, whenever dog places over to robot, then we can return certain response, and we can say, okay, this is a kind of illegal person or a robot found position, found response, and we can end the episode as well. And for all these other valid movement, we can return the response similarly. So for the sake of visualization, I have avoided writing all the code here, but I will show you at the end of the session what I have written exactly in these methods. So in these slides, I have avoided, or basically given the comments to give you the idea like what works in these methods. So I will show you the whole code by the end of this session. So this is that's all for a game logic class. Now second step is TFagent environment, creating a TFagent environment. So like I said, we have these two diagrams here. We have just implemented game logic class. Now we need to implement TFagent environment, and to do that, let's look at the higher picture here. So we have init method, like in the case of logic class, we have reset method, we have a step method that will essentially tries to take each step in our game environment. And this move dog this step method will use this move dog method that we just created earlier, and by observing the response from this move dog position, move dog method, then we will give whether to give a penalty or reward or end the episode. So we can programmatically use that here by using this method in this TFagent class. So the way we create this TFagent class is by inheriting this by environment from TFagent. So under TFagents, when you import TFagent, then you can import by environment. Under by environment, you can use this by environment here. And this init method here, this will act like how we want to import the state of the game, and how we want to create this specification for our environment. So by specification means like we just created a 1D array for our game, right? The environment there, but we need to specify so that the TFagent framework also knows what goes in each portion of the environment and what's the size of the environment. So this let me go with this. Okay, so this observation spec, the observation specification will tell us to tell this TFagent environment class that, okay, we have a 1D array with 36 person, and each person is an integer, has an integer value, and the maximum value in each person is from 0 to 3. So the environment will cannot have more than this the value of 3. And similarly, in action spec, we also need to create a specification for the actions that the agent can take. So the value the agent can take is a maximum from 0 to 3, and each value is an integer. And what it means by each value from 0 to 3 is can be defined by this dictionary, where we can associate each value with a position the dog we want to move. So for example, if the dog chooses the action of 0, then we can say, okay, let's move left. And if the dog chooses to take action of 1, then we can say, okay, let's move the dog to right. And similarly, 2 for down and 3 for up. And you can see for left and right, we have just basically moved right or left position from this array, and from up and down we have just added and subtracted the position of 6, because if we reshape the 1D array of 36 into 2D array, then we can say in each row there are 6 positions, and we can basically move up and down with 6 position with this action. And similarly, we can import the game state from the earlier game logic. So in this case, the game is actually the object we created earlier, the game logic class, and we are just inheriting it. We're just associating with. And similarly, with after init, we can create a reset, and this reset will basically call the game logic reset method, and it will basically reset the environment to the initial position, and the episode will start again. So by calling this time step and time step restart, this will set our game logic, our game state to the earlier one, and reset the episode. Sorry about that. And similarly, we have some custom method here called action spec and observation spec that will basically return the action spec and observation spec. Okay. And now we have a step method. So this step method is analogous to the move dog method that we created earlier in our game logic. So if we go back to this example, we can see that this step method will call this dog move method. So what we are doing in this step method is that first we are passing the action that has taken by our agent. So this action can be integer of 0, 1, 2, or 3. And what we are doing here inside this step method is translating that action from 0, 1, 2, 3 to a certain position where we want to move the dog by using the dictionary that I showed you earlier. And after that, we know the next position that we want our dog to move. So basically what we can do is we can pass the current position and the next position of our dog to this move dog method of this game logic class. And by observing the response, the return from this method, we can associate reward to the agent. So in this case, when we translate our action to the position and pass that to the move dog method, we can say if the response is illegal move, then end the game with a penalty. Similarly, if the response is a found robot, end the game with a penalty. If the response is found ball, give a reward and transition the game to the next state. And similarly, if it is a normal valid move, then give a small penalty so that our dog will know the dog needs to complete the game as soon as possible and transition the game state to the next state. And that is all you need to do to create an agent, an environment in TFAgents. So after that, what we can do is we can basically wrap that environment to a TensorFlow environment module here by TFPy environment, which is also comes inside TFAgents. And we have our environment, our TFAgent environment. So what we are doing here is that basically we are passing our game logic inside the TF environment that we earlier created, and the object is now wrapped inside TensorFlow Pi environment, so that TFAgent can use TensorFlow with the environment that we have just created and create the environment to train our agents. And this line, this utils.validatePy environment, acts like a test so that it will check whether we have coded the environment properly or not. So it will test if the reward is acting properly or not, if there is like a logic error inside our classes in this environment. So this is basically check if all the things is working as expected or not. And we can test it by a number of episodes, and if it returns nothing, then it means it works. So with this line of code, we can easily create our environment. So far what we have done is we have created a TFAgent environment that has our game logic, and that has logic for giving reward or penalty, ending the game, and transitioning the game to the next state. Now let's create the agent, the learning agent that we use in this game environment. And the learning agent that we use here is a DQN or DQN agent, and we can easily create a deep Q network, a deep neural network for Q learning in TFAgent by using this module called Q network inside TFAgent. So here you don't have to create a Keras model that has all these different layers and activation and things like that. You can easily create that by passing those things as a form of argument here. So in this case, I have a deep Q network here with 3 hidden layers, and each layer has this hidden units. So first layer has 32 hidden units, second has 64, and third has 128. And we can easily create that neural network using this Q network module, and we can pass them as a form of argument here in TFAgent. And with this line of code, we can easily create our DQ network, QNet, basically. So here, as you can see, we need to provide our deep Q network observation of our environment and the action spec, what kind of action our agent can take. And then we can provide the number of hidden layers. Here in this case, I have provided number of fully connected layers, but you can also provide convolutional layer in as a form of argument. And you can also provide what kind of activation you want to use in each layer as a form of argument as well. And of course, you can provide optimizer that can be Keras optimizer, so tf.keras.optimizer, and that can be a Adam optimizer or RMS prop optimizer. And after that, you wrap them all in your DQN agent using this line of code. So basically, you provide your environment, your training environment, and the time step spec, the action spec, and the Q network you want to use to train your agent, the optimizer. And if there are other hyperparameters that you want to pass, like epsilon value and things like that, then you can pass them that there as well. And after that, you initialize your agent. And with this line of code, you can easily create your DQN agent. So first we created our TF environment, then we created our TF agent that works for this environment. So one thing I missed here, so while creating this environment, is that if I go a little bit backward, so here I have two environments, training environment and eval environment. So basically, while creating an environment and training our agent in our environment, we basically create two environments, one for training and one for evaluation. And they are essentially the same environment, but the states of the environment are different in each case. So that's why we want to like separate out this different environment here. And after that, okay, so let's go back to the diagram of our TF agent. So far we have created environment and agent. So let me go back to this diagram of TF agent. Oh, okay, I think. Let me go back here. Oh yeah. Okay, so this is the higher level diagram of TF agent. So we see that so far what we have done is we have created our environment here, and we have created our agent, which uses a policy model. So policy is basically how our agent takes certain action. So in this case, our policy model is the Q network that we just created. So this Q network will act like a policy that will drive our agent. So the policy, like it sounds, is how our agent should work or take action in an environment. So our Q network, our deep Q network, will act like a policy to our agent. So far what we have done is created this module, this component, and this component. Now we need to fill out all these components to work in TF agent. So first, let's head back to replay buffer. So how we are training our agent in TF agent is by providing them with the past examples of how things turn out while taking certain action in the environment. So to do that, what we create is called replay buffer or replay memory. So like the name suggests, replay memory will consist of past transitions or past states. So whenever the agent is taking left action or right action, or taking different actions in an environment and transitioning the states, so all of that information of a reward, the state transition, the different action taken by the agent, they are all can be stored in a memory called replay memory or replay buffer. And by using that replay memory, we can train our agent. And so we need a place to store all these past activities that are performed in an environment by our agent, and using that activities, that past steps that our agent has performed, we can train our agent so that in future it can take better action by observing certain reward or penalty in the past. So to do that in TF agent, how we create replay memory is by using this TF uniform replay buffer. And you can basically provide the agent information. In this case, how the agent collects certain specification using this agent.collect data spec. You can also provide the batch, number of batch, size of the batch of to take while collecting all this memory. So in this case, train environment batch size, and you can specify how big your memory should be. So in this case, I have set this number to 1 million. You can also create this to even more or even less, but for the better performing, it is suggested that you make the size of the buffer as big as possible. And using this, you can simply create replay buffer or replay memory. And one other thing that we have in this diagram is called observer. So observer is basically a function, and this function will allow our past actions that are taken by our agent to be stored in this replay memory. So in this case, observer is replay buffer that we just created dot add batch method or function, and this add batch function will basically collect the past action taken by our agent in this environment and pass that to our replay buffer memory. So so far what we have done is we have created our agent, our environment, our replay buffer, and the observer function that will add this past actions taken by our agent to this memory. Now let's set some training metrics. So this training metrics will help us evaluate our model or our learning agent while training them. So in this case, we have two training metrics that are average return metric and average episode length metric. So average return metric will give us the idea that while training our agent for multiple iterations, in average, how much is the value of a return in each episode. So whenever an episode ends, what is in average the value of each episode. So we can train our agent for multiple iterations while training our agent, and using this average return metric, we can observe how good is our agent performing. And by observing this average episode length metric, it will give us idea that how many steps our agent is taking in each episode just after completing it. So for example, in earlier case, whenever our dog accidentally places himself over to the robot, then the game will end. So if the dog takes one step and he accidentally steps over to the robot, and the game ends, then that the average episode in one iteration in that will be 1. So while training our agent for multiple iteration, if the average episode length is not too high and not too low, and just in between certain values, and the average return metric is also significantly large, then we can say that the training process is going good, because even in the fair amount of step, our agent is our agent is accumulating as much return as possible. After that, we create drivers. So when we look at this diagram here, so what we want is that to take certain action in our environment, and that action can be later on stored in our replay buffer. We need driver. So driver is that component that will allow our agent to take certain action in our environment, and while doing that action using this observer method, we can add them to our replay memory. So driver is just that. So in this case, in TFAgent, there are multiple drivers. One of the driver is dynamic step driver, and that will help our agent, that will use our agent policy and take certain action in our environment, and while doing so, we can pass the observer that we want and the training metric we want as an observer, so that while taking certain action, these actions can also be later on stored in the memory, and that can later on be used to train our agent. And at the same time, while taking that action, we can also know how good our agent is performing by using the earlier metric that we just created. And we can initialize our driver by how many steps that we want to take our agents, and things like that. These are all hyperparameters that we need to specify. Now we know that in this diagram, what we have done so far is that We have created environment, driver, and this driver will use the policy that is the neural network and collect some trajectory or the states, action pairs, and things like that. And this can be used to store in our replay memory using the observer, and later on using this replay buffer or memory we can again train our agent. So while just starting the training process, we might not have anything in this replay buffer because this will be like an empty thing right now. So to avoid that step and to have certain value, certain past transaction trajectory in this replay memory, what we can do is we can create a dummy random agent that will take certain action randomly in our environment, and we can create a driver that will collect this random action and store them there in this replay memory, so that while just starting this training process, the replay buffer will not be empty, and and our agent will have some past trajectory to be trained on. So to do that, what we have done here is we have created a random TF policy that will take random action based on our action spec, and this will help out to collect certain steps using the driver and store them in the replay memory, so that when starting the training process, the replay memory will not be empty. So after that, what we can do is we can simply use our replay memory as a TF dataset. So using this replay buffer.as dataset, we can simply specify the batch size, the number of steps that we want to take in each batch, and we can also specify the number of parallel calls and prephase numbers and things like that. And we can simply specify our replay memory as a TF dataset and use that to train our agent. And let's train our agent. So for the sake of simplicity, I have removed the code in the slide, but I will show you what I have done to train the agent. So by now, what I want to say is that I have trained the agent for like 150,000 iterations, and after that I got this result. So in this case, we have used two metrics here. One is average return and another as average episode length. So so we can see from this graph that it's not an ideal graph, but we can see a general progression in learning. So our agent learning the reward, the maximum average return or reward that our agent can accumulate in each episode in average was this low, but soon when we repeat the iteration, it is learning something, and now we have a final reward around this point. And similarly, the average episode length is also a little bit increased from 0 to this one. So we can say somehow our agent has managed to learn something in this environment. And let's see how well our agent will perform. So let's evaluate and visualize our agent. So we know that we have created this environment as a 1D array, and we have given numbers like 1, 2, 3 for our dog, bone, or robot. But we can, while visualizing the steps in our environment, we can simply reshape this 1D array, this observation of our environment from 1D array to 2D array, and we can simply replace this number 1, 2, 3 to certain icons that will represent the state or the player of our game. So what I have done here is that simply I have run our game eval environment for one episode after training our agent, and in this case our agent took 14 steps to complete a game, and by the time it reaches to 14 steps, it has manages to put himself at this end position. So we can see from this diagram that at the end of this 14th step, the final reward the agent has managed to collect is 12.6, and it has successfully avoided all these positions of dog, all this position of robot, and manages to collect as much bone as possible and reach this end position. So all these steps are also described in a blog post in this Medium publication, which is called Deep Learning Journal. And the title of this blog post is Train Your Dog Using TFAgent. And let me just show you the code that I have avoided in the slide, so that it can give you a bit of a more idea of how I have managed to visualize all these steps and train the agent. So let me go back to this GitHub, and you can find this link on this blog post here. So this is the original blog post this session is based on. So if you read this, you will have even more idea, and I have basically explained the same things as in this session. And if you want to read it, you can go ahead and read it. And I have also written all the code here. And by the end of this article, you can see the link to this GitHub notebook. And here I have used this the same notebook I have used to train the agent. And if we go to this section, so this is the game logic class and the move dog method that I have created. So as you can see here, what I have done, what I'm doing here is that I'm just checking if the next position is the last position or not. And if it is the last position, then simply replace the current position of our dog to an empty position, and place our dog to the next position, and then end the game with a response of game complete. Similarly, if the position is out of bounds, then return with a response of illegal move and end the game. And if the position is a position of a robot, then end the game with a proper response. And similarly in case of bone as well. And if the condition doesn't satisfy, then simply we can say it's a valid move, and return the response as valid move. And in case of TFAgent environment, I have simply checked that. So if the response from our move dog is a game complete, then simply terminate the game. And if it is also illegal move, then terminate the game with a reward of minus 0.3. And if it is a response of found robot, terminate the game with minus 0.3. And but if it's a bone, then give a reward of 1 and transition the game to the next state. And similarly, if it's a valid move, then just give it a little bit of penalty, so that we will train our agent to complete the game as soon as possible and transition it to the next state. And to train our agent, you can go to this code. So basically, what I've done is that I have created an iterator around this TF data set that I have done, that I have created using the replay buffer. And I have just simply extracted out some trajectory from this data set and use it to train our agent, and evaluated the metrics that I have used to evaluate the agent while training it. So basically, while training our agent for 150,000 iterations, we can see all this metric values here. And let me go to this end section here. So this is the final graph for the training. And to visualize our one episode of evaluation, what I've done is that I have simply taken out the observation from our game environment, the evaluation environment, and I have simply reshaped it to a 6x6 array. And I have simply replaced the number 1 with a dog, and number 2 with the icon of a robot, and number 3 with icon of bone. And if it's a 0, then it should be an empty position with this one. And using these functions, I have simply evaluated our agent in this eval environment for one episode. And you can see all the steps that the dog has taken to complete one episode. And we can see by the end of this step 14 and taking action of 3, the dog has managed to complete the game with a final reward of 12.6. And I have also created a blog post for the second part of this blog, and it is called Train Your Dog Using TFAgents 2, and it's called Revenge of Kiko. So in this case, what I have done is I have created one extra player here. So now our DQN agent will not only train one player but 2 players, and this cat will help our dog to complete the game even faster and collect more reward. And to make it more exciting, I have also trained our players to not just avoid the robot but attack the robot. So whenever the dog takes certain sneak attack move, like moving diagonal from certain position, then the dog or cat can attack the robot, and that will also give extra reward. So by the end of this blog post, you can also see that the agent has managed to let me go at the end. So the agent has managed to complete the whole game in 18 steps and with a total reward of 19.3. And you can see all the robots are gone now, and it has managed to collect as much bone as possible. So yeah, so that's it for the session. So let me just share you some of the resources that you can look into if you want to learn more about reinforcement learning. So obviously, if you go to tensorflow.org/agents, you will get a lot of information regarding TFAgents, and I highly recommend you to check all these videos. They are very excellent, give you in-depth idea of how this TFAgent works. But a bit of disclaimer here: this TFAgent is very early in its version, and there are still a lot of materials that are severely lacking. And if you are familiar with deep reinforcement learning, and if you are also interested in working with TFAgent, then you can also contact me, and we can work on the tutorials or blog posts or something like that using TFAgents, and we can collaborate or whatever. So I highly recommend you to go to this URL as well. And I suggest you to read this book, because this is an excellent book. And to be honest, this book has given me the primary idea more easily than I could gather from anywhere else on the internet. So if you go to the chapter 18 or 16 of this book, there's a chapter for reinforcement learning, and I think if you complete that chapter, you will get all this overall idea, how reinforcement learning works and how we can work with different frameworks, not just TFAgent but other frameworks as well, for deep reinforcement learning and so on. So I highly recommend you to get this book and read it. It's an excellent book. And another is a free resource. It's in YouTube. It's inside this DeepMind channel. It's called Reinforcement Learning course that DeepMind has conducted with UCL. And this will give you a theoretical idea on how reinforcement learning or deep reinforcement learning works. And if you're like me and if you like to read from a book, then here's the good news. This book, Reinforcement Learning Second Edition by Richard Sutton and Andrew Barto, is a free book you can get right now. It's a second edition, I think. And you can, I think, if you manage to complete the whole book, then I think you will have an excellent idea of what reinforcement learning is and how you can, deal with this field and contribute to it and help it advance even further. And if you like to learn from videos, then fortunately there is a course or specialization in Coursera called Reinforcement Learning Specialization, and this specialization is also based on this book. And even in some courses in some week, you can actually see the authors giving idea on different topics of reinforcement learning. So for example, temporal difference and things like that. Richard Sutton himself has conducted certain lectures there. So I highly recommend you to take this course as well. And by taking this course, you will also read this book as a reading material, and so it's the best of both worlds, I guess. And that's it. Thank you so much. If you have any question, feel free to ask.
It was amazing. I was like really nice overview and good examples, right? So it started kind of like simple, but I think you showed like many different aspects of that. So definitely like hats off for this.
Thank you so much.
Cool. So I guess like people still asking some questions, but I will just like start with a couple of simple ones. So you mentioned that for your replay buffer, right? You had like 150,000 episodes. How long it took you basically to collect it, and also how does it look like for more complex environment, right? Can you run some of environments like in parallel, or like what is the general setup basically for that?
Yeah, so I used Google Colab to train this particular game, and it took me around 10 minutes or so to train the whole agent for 150 iterations. And I think it depends on the number of layers that you use for a deep Q network as well, of course. And and the complexity of the game itself. And sometimes the game, the learning algorithms that train faster, but it doesn't necessarily mean that it will train better. And it's very tricky. As you can see in the final graph, it's very noisy, and it's very hard to get a better graph, that can get a better agent. So it's highly dependent on hyperparameters, and I think I just got lucky in some parts to get that kind of a graph as well. So I think it's very challenging. And I'm to be frank, I'm not also sure like what set of hyperparameter works in this particular case, because I tried many of them and it happened to work like that.
Yeah, nice. Sounds cool. Maybe another question. So you brought us like a very nice for learning example with the dog ride. And I mean, there's also like robotics that are like, you can collect some examples of that, right? Do you have any more practical, let's say, applied examples? Because I heard there's like in finance, they do it right, or in Switzerland, I think they do like for train scheduling, right? Have you heard about anything else that people use reinforcement learning in more like a practical business cases?
Yeah. Of course, finance, trading, they are all like you can get top of your head. Like these are like the examples that you get. I think here's this experience that I got. So while taking one of the course in Coursera in this specialization, there is a task that you are like given to frame certain problem in terms of reinforcement learning. So all of these learners and participants, they try to frame certain toy kind of example in a reinforcement learning setting. So there are certain examples like we can create a robotic arm that are trained using reinforcement learning. So basically in reinforcement learning, what you need to do is you need to define what is a state and what are the rewards and what are the actions. So if you manage to break any task into all these three sections, so what will be the state? So in case of a robotic arm, it could be like a position of your arm or something like that in each state. So while moving, it could be like this angle or this position. And what could be the action? So it could be like a voltage applied to each of the joints and things like that. And what could be the reward? So if the robot arm manages to pick something up and manages to drop something in another place, then that could be a one reward, and if it not, then that could be a negative reward. So similarly, if you can break down every task into this setting, then I think it works for reinforcement learning.
Yeah, makes sense. I guess it's also kind of like following up on creating a proper environment, right? So like for action, you get what is the reward. Sometimes it's hard, right? Because even like a trading, you said, you can definitely replace the cases that did happen, right? But if agent is taking the case that didn't happen before, right? You need to have a model of environment, right? And if you kind of build model of trading environment, you kind of know how trading works already, right? So you know what I mean? It's a bit of a chicken and egg problem in a way, right?
Yeah. So there was this example like how do you measure effectiveness of a thermostat or something like that using this setting? So one analogy or one example can be like if a human needs to correct the thermostat by himself, then that could be a penalty. And if the thermostat works and for a longer period of time, human doesn't need to interfere, then that could be a reward, So yeah, of course, these are like it's a very emerging field and things can be challenging, but this are like very interesting take on this learning algorithms and a different thing that we see in machine learning or deep learning. That it's a different set of mindset that we need to develop.
Yeah, nice. So we got another question from Matthew Masters, and he's asking like why replay buffer cannot be empty basically when you start training.
Okay, so the agent is actually learning from replay buffer, and when we start the training process, if it's empty, then it will fail. So actually, the first step of training is the replay buffer will take the past transaction and convert it into TF data set, and that will pass to the deep Q network. And by evaluating and doing certain action, that will be a certain policy for that agent, and using that policy only, then the driver will work to collect furthermore transaction and add it to the replay buffer, so that it should not be empty while training the agent, because the agent needs to train from the replay buffer. So avoid that. To avoid that, we have created some random actions to just fill it up the replay buffer, so that the first step will not be empty.
Is there like any way to do, just like a random question, right? But is there like any way to have like a pre-trained, kind of almost like a transfer learning setup, right? So initially you already have, okay, like your saved agent, right, in a way, right? And after you kind of just transfer to the new events, or is it just like too complicated?
Yeah, no, I think it is possible, and I have also tried some of the experiment with that. So while preparing the second part of the blog post to add another cat, so what I have done is that I have trained parallelly two agents in a different replay buffer, and but they have the same environment, they have the same reward function. So what I have done in one of the experiment, which I haven't used in this blog post because it didn't work properly, but the setting works. So what I have done is that I have trained parallelly one agent and use that policy to trigger, to collect using the driver to collect to the replay buffer, and so that works. Yeah, and actually I think that is also a good way to train a new agent, because if you already have an agent that is again already working, then you can use that agent to fill up your replay buffer and train from that, so that the next agent will be even better than that.
Nice. So the only question how you would afterwards redistribute the gradients, right? So once the two different agents learning, right, you can still like merge those like learnings like into some general policy.
You can almost do like adversarial things. So one agent is trying to increase certain reward, and another agent is trying to increase another reward, and you can use both of the agent to gather all this replay buffer trajectory and use the third agent maybe and things like that.
Nice, cool. Maybe, okay, so a different question. So like in the beginning, right, you had this training environment, right? And there's like validation one, right? Is it a common setup, right? Or sometimes you have an environment just like with randomness, and after you cannot really overfit, right? Because environment itself, let's say if you have like a robo hand, right? So does all of those like movements, right? Would you also have like a training hand, right? And after validation one, right? Because if you can solve the robo hand, right, it doesn't, you don't really overfit, right? You're just like solving the problem, right? How is generalization versus like overfitting for such a like environments, basically?
Yeah, I think that's an excellent question. I'm also not sure about that particularly in case of a robot hand. But in case of this game environment or other game environment, typically we are using different setup to validate our agent. But like in the physical terms, I'm not sure, to be really frank, and that should be like over expensive to have a different set of environment as well. So maybe so when we are using the real environment to train our agent, then maybe we don't need to use the different set of environment, because if it works on the environment, then it works, right? But I'm not sure. That's just a thought.
Yeah, makes sense. And just like the follow-up, if you use like a doc example that you brought, right? Did you randomize your environment, right? So like other bonds, like always in the same position for all 150,000 cases, and if you would randomize, would it work? Or because I mean, at the end of the day, it still receives like inputs where the like all space is, right? How do you think?
Yeah. So in this case, it's a fixed one, and even if we somehow randomize them, I think it will be a little difficult to train, because even in this setting, using this particular algorithm, the DQN, it was quite hard, to get to a point where it could, accumulate like 12.6 final return at the end of the episode. And if you randomize all these rewards, well, in case of reward like bone, then it should not matter. But in case of robot, if we randomize them and it doesn't exhibit certain pattern while moving around in each episode, then I think that will be a bit challenging for our agent to catch on, because by definition, random is kind of like unexpected, and it can be anywhere, right? So if it like if it is not like exhibiting any certain pattern even in randomizing the movement, then
Yeah.
I think I think it's very challenging. It's like a minesweeper or things like that.
Yeah, no, makes sense. And maybe there's also somewhere in the middle where you randomize between like game generations, right? But not between the steps, right? So the robot is basically staying in the same position. Because what I'm kind of was thinking, like, what is stopping robot, right, to just learn ideal static policy, right? Your steps, given like my current condition, right, and the map where I should be doing, right? Because here's you can just solve it once, right? And you don't need to even like act, right? You remember the trajectory, right, of the most winning one, and you can just stay there.
Yeah.
Cool. And while we were talking, we got like another question from Ivan Rodriguez. How do you choose the DNN? Is reinforcement learning algorithm highly dependent on the DNN?
Yes and no, I think, and even in this particular set of DNN that I have used with just fully connected layers, I developed this unofficial, and I think it will not be a right strategy to develop such algorithms. So while we're playing with all these algorithms, and as this game is a very small one, the lower number of neurons in each layer, like in case in this environment I have only three, in this DNN I have only 3 hidden layer, and in each of them it's not more than 128. So in every experiment I tried with a larger number of neurons, the training is highly like noisy and fluctuating, and it kind of like behave worse than even the lower one. And I don't know if it's the complexity of the game or the algorithm itself that it uses to train the policy. So I think it depends on the environment that you are trying to train. So in case of a like a game like a Breakout or a 3D game, maybe you need to use a convolutional neural network, because in this case it's just a 1D array and I can easily pass it to the DNN with a fully connected layer, right? So Breakout and things like that, you can use convolutional layer, and if the rule of the environment is a bit complex and there are a lot of obstacles, then this particular set of example in this case of game, then maybe you need to choose a larger architecture. But in case of simpler one, maybe try to use the smallest architecture as possible. That is why I have used the even I have trained in one of the experiment I have trained on 8 neurons, 16 and 32 neurons, and somehow it manages to work quite well. And so yeah, it's like I said, these are all hyperparameters, and it's very tricky. And one thing, it's tricky to be in deep learning, and it's a next level in deep Q network, because you don't know like where things can go wrong.
Nice. Yeah, sounds good. So maybe like last question from my side. What is next up for your like reinforcement learning and TFAgents? Do you see like some things that, I don't know, you're going to build your own tiny robot like in real world, right? Or like what are your plans?
For now, I'm just exploring a lot of algorithms, because there are a lot of papers and research out there that I'm also quite not sure how to comprehend all of that, because in short span of time there are so many research. And right now my biggest like concern is to try to understand the basic of most of the algorithms that are like advancing in each year, and try to keep up with it. And I like I said, the TF agent itself is very early phase, and I'm also not sure where it's heading, because but the architecture it has proposed is quite nice. It's nice to train an agent and things like that. But I also like to suggest some flexibility in terms of a lot of things while implementing algorithms. So my current task or my steps in reinforcement learning to try to comprehend all these algorithms, and especially in case of multi-agent environment. So all of the agent that I have trained or showed in this session is a single agent. So how can I incorporate a lot of multi-agent environment, and how we can effectively collaborate between each of them and try to solve complex tasks? And that is the most, I think, the exciting task. And right now I'm not so much concerned about robot, but more into like software and multi-agents interacting with it maybe.
So Skynet maybe, or not, let's see. Awesome. It was a blast having you, like really great
Thanks so
presentation.
much.
So yeah, let's wrap it up here and see like if somebody going to ask questions like in a hangout, like for another 10 minutes maybe, and we are done with that.
Yeah.
Awesome. Thank you. Talk to you in a bit. I will send you a link.
Bye. Thanks so much. Bye,
Thank
everyone.
you. Let's stop the stream and broadcast.